Okay, here's another example. Solve cotangent of x cosine squared x equals 2 cotangent of x. Okay, so notice we have two different types of functions, so you're going to have to figure something out here. So one thing I can do is to subtract this 2 cotangent of x onto the other side. And then notice that I have this expression here where I have a common factor of cotangent of x. I have a GCF of cotangent of x. So I can pull that cotangent of x out to the front. So here I've factored out that cotangent of x. So this is a step where it tends to confuse some students. Just visually, I think they're like, what? How did this happen? Well, think about it. If I were to take these two parts, because I have something minus something, and they both have cotangent of x in common, what do you get, right? If you're pulling out the cotangent of x, what do you get if you divide this first chunk by cotangent of x? What are you left with? You're left with a cosine squared of x, right? What do you get? What are you left with if you divide negative 2 cotangent of x by cotangent of x, right? Because you're dividing by cotangent of x. What do you get? You're left with negative 2. Okay, again, notice if I were to distribute, you would end up with cotangent times cosine squared x, and then minus 2 times cotangent of x. So these two expressions here are equivalent. They're just in different forms. One has the cotangent of x multiplied out. The other one has it pulled out in the front. It has it factored out. Okay, so I've factored out my cotangent of x, but what can I do now? I hope you can notice that I have something times something equaling 0. So I'm able to use zero product property. The zero product property is when you're multiplying things together and they equal 0, then each of those parts, or at least each of those parts, must equal 0, right? So you can set each factor equal to 0 and solve. So this is almost like two separate questions in one. So for cotangent of x equaling 0, right, cotangent is going to be your x over y, since tangent is y over x. You look from 0 to pi, right, because for cotangent and tangent you always look from 0 to pi to see where you would get 0. Okay, that happens at the angle pi over 2, right, because at pi over 2 you get 0, 1. So if you put 0 over 1 you get 0, right, at the angle 0 you would get undefined. So it happens at pi over 2, but I'm going to go ahead and put plus n pi since we're solving for all possible solutions, right? They didn't say to solve within specific intervals, so you're going to have to solve for all the possible solutions. Because it's cotangent, I've added the n pi. So for that second factor, I added 2, right, and then I to the other side, and then I take the square root of both sides, getting cosine of x equals plus or minus root 2. So you would normally look at your unit circle from 0 to 2 pi and ask yourself, where does your x equal positive root 2 and negative root 2? However, you need to remember something here. Remember that the cosine function, its ratio as well as the sine function, must be between negative 1 and 1. And root 2, right, root 2 is greater than 1, right, or negative 1 in the negative direction. So this is not possible, it's undefined, so you would have no solution in this case. You have no solution in this case because there is no angle that you can plug in such that when you take the cosine of it, you're going to get a number that's greater than 1 and less than negative 1. So you get no solution for this second factor. Therefore, your final answer is just this here. Pi over 2 plus n pi. Any angle that is pi over 2 plus n pi, so you can, like, n could be like 0, or it could be 1, it could be 2 in the positive direction, but it could be, n could be like negative 1, negative 2 in the negative direction. If you were to plug that in there and add it to pi over 2, right, those are the angles that would make this original equation true. Go ahead and try this problem. Find all solutions of 2 sine squared x minus sine of x minus 1 equals 0 in the interval 0 to 2 pi. So here you would want to factor. So if you had 2x squared minus x minus 1 equals 0, right, you would factor as 2x plus 1 times x minus 1 equals 0. And then replacing it with the sine function that you actually have, this is what you end up with. So this is like stuff that you saw in 5.1 and 5.2 where you had to simplify the left-hand side, in this case by factoring. And now we have two factors equaling 0. And then you can set each factor equal to 0 and solve. So in this case, if I subtract 1 and divide by 2, I get sine of x equals -1/2. Here, if I add 1, right, because I set the whole thing equal to 0, I get sine of x equals 1. So then now you're asking yourself, in the interval 0 to 2 pi in your unit circle, where does your y value equal -1/2? And here, at what angle does your y value equal 1? Okay, and these would be the angles, right? So you have 3 solutions to the equation. Go ahead and solve this equation. So you'll want to simplify the left-hand side first. So I notice that sine squared x I can replace with 1 minus cosine squared x, since the other one's in terms of a cosine. And when I distribute the 2, I end up with 2 minus 2 cosine squared x plus 3 cosine of x minus 3. And then when I combine like terms by doing the 2 minus 3, I end up with a -1 here. But because I want that leading term to be positive, I just divided both sides by a -1, or multiply both sides by -1, or you can think of it as just adding everything to the other side. So all the signs switch, and I end up with 2 cosine squared x minus 3 cosine of x plus 1 equals 0. Now I have it in that quadratic form, so you can go ahead and factor. So you can see that in that quadratic form, if I were to factor, I get 2x minus 1 times x minus 1 equaling 0, and you can replace the cosine back in. So, and then set each factor equal to 0 and solve. So this is your final answer here. Pi over 3 plus 2n pi, 5 pi over 3 plus 2n pi, because these are cosines, you're going to add that 2n pi since you need to solve for all the solutions possible. And then 0 plus 2n pi. So you have that 0 there, so in the textbook for your final answer, you would normally see it just as 2n pi, since that 0 you don't usually write there. But you can keep it as 0 plus 2n pi, you would still get full credit. Lastly, we're going to look at functions involving multiple angles. So these are the problems where you're going to see like a coefficient in front of the x. So you might see something like, sine of kx, meaning like sine of 2x, or sine of x over 2, where the coefficient is 1 over 2. So for these types of problems where you have a coefficient in front of x other than just +1, the way you solve these problems is to solve the equation for kx. So like you would solve for 2x, right? Or you would solve for 1/2 x, or k over 2, x over 2. And then you just isolate the x by dividing your result by k. So in this case, you would divide everything by 2, right? And that would be your final answer. In this case, you would multiply by 2, because you're dividing by 1/2, which is the same thing as multiplying by 2. You're just basically trying to get the x by itself. So you would like multiply the whole thing by 2. Okay, let's take a look at some examples. Here's an example. Solve 2 cosine of 3x minus 1 equaling 0. So when I add 1 and divide by 2, I end up with the following. So notice that like my k value, my coefficient is 3 in this case. So remember the directions were to solve for this entire thing, right? The kx, whatever that is, solve for it. So what would that equal? Cosine of what equals +1 over 2? Again, because it's cosine, we're just looking from 0 to 2 pi, and you're looking for, right, circuits or tykes, where your x value is +1/2. And your x value, your x coordinate is equal to +1 over 2 in quadrants 1 and 4 at pi over 3 and 5 pi over 3. So I write that in. Notice that this is just solving without a specific restriction. So you're going to have to also do plus 2n pi to account for all the possible solutions. Okay, so again, I've solved for the kx, in this case 3x. And then, because I want to get x by itself, I'm going to go ahead and divide by 3 on both sides, right? I want to get x by itself. Well, dividing by 3 is the same thing as multiplying by 1/3. So if I divide by 3 here, I'm going to multiply that by 1/3. I get pi over 9. And then if I divide this by 3, it's just going to be 2n pi over 3. So you guys see that pi over 3 divided by 3 is the same thing as pi over 3 multiplied by the reciprocal, giving me pi over 9. Okay, so this is one solution. And then the other solution is the same thing. I'm going to go ahead and divide all of that by 3. So I get 5 pi over 3 times 1/3, giving me 5 pi over 9, plus 2n pi over 9. Again, if you see that coefficient other than 1 in front of that x, you just solve for that kx, right, the 3x in this case, and you just divide by whatever that k value was to isolate the x. Okay, go ahead and try this problem. Solve 3 tangent of x over 2 plus 3 equals 0. Notice that your kx in this case is x over 2, or like 1/2 x. So you ask yourself, where does tangent equal -1? Because like you just think of that, right? Like tangent of what equals -1, and you only look from 0 to pi because that's the period for tangent and cotangent functions. So x over 2, right, because you're solving for that, that occurs at 3 pi over 4. And because it's a general solution, you're going to have to tack on plus n pi to account for all the different possible answers possible. And in this case, to get x by itself, we would have to multiply by 2. So your final answer would be x is equal to 3 pi over 2 plus 2n pi. Or if you didn't reduce, right, you would get 6 pi over 4 plus 2n pi, which would also give you full credit. But the reduced form is the preferred form. This answer represents all the answers possible that could go in for x that would make the original equation true. Okay, just to recap, if you had to find all the solutions for cosine sine and thereby secant cosecant, you look in the region 0 to 2 pi. So you look in all 4 quadrants and then you add plus 2n pi. If you have a tangent and cotangent function, then you just look in the first 2 quadrants from 0 to pi, and then you're going to add n pi. So you're going to put plus n pi.